Staying on top of the technology shaping our world can feel like a constant uphill climb, can't it?
It really can.
Databases, data management, it's a vast and often complex landscape.
Definitely.
Think of this deep dive as your expertly guided shortcut. We're here to extract the essential insights, uncover surprising connections, and hopefully spark a few of those satisfying aha moments for you without, drowning you in unnecessary detail.
Exactly. Our focus today is to illuminate the core principles of databases. We'll be exploring how to structure data effectively through normalization, harnessing the power of SQL to interact with that data, and understanding some fundamental related concepts that underpin it all.
And we've got a rich set of resources fueling our exploration today. Imagine having a carefully curated collection right at your fingertips.
Yeah, quite a mix.
We're drawing from the foundational knowledge of, say, MIT OpenCourseWare, getting practical perspectives from industry-standard documentation like MongoDB's, examining real-world best practices from platforms like StrataScratch and Metabase, and even tapping into the collective experience shared in discussions about SQL dialects. It's quite a range.
It really is. We're synthesizing information that ranges from academic theory to practical application and, the lessons learned in the field.
Right.
Our aim isn't to turn you into a database expert by the end of this, obviously, but to provide you with a robust understanding of the key ideas that drive this critical area of technology.
Okay, let's dive right in then. First up, a concept called database normalization. It might sound a bit intimidating, like something out of a science lab, maybe.
It could have that formal sound to it, yeah. But at its heart, normalization is simply about organizing your data in a sensible way.
Okay.
To minimize redundancy and ensure consistency. Think of it as establishing a well-organized system for your digital information.
So what kind of disorganization are we trying to prevent here? What's the problem?
Well, one fundamental issue that normalization tackles is the use of variable length lists or repeating fields.
Repeating fields, like...
Yeah, imagine trying to track the vehicles used by drivers by having columns like Vehicle 1, Vehicle 2, Vehicle 3 in your driver's table.
Okay.
The MIT notes pinpoint the inherent limitation. No matter how many vehicle columns you create, you'll inevitably encounter a driver who uses, one more.
Right. You'll always need just one more column eventually.
Exactly. This simple limitation underscores a fundamental principle of database design. Anticipate change and build flexible structures rather than being constrained by fixed assumptions about your data.
That makes perfect sense, the never-ending need for just one more field. So what's the more adaptable solution?
So the elegant solution is to employ many-to-many relationships.
Many-to-many. Okay.
Instead of those rigid vehicle columns within the driver's record, you create separate entities for vehicles and drivers and then use it like a linking table to clearly define which driver uses which vehicle. This approach is far more flexible and avoids the inherent limitations of a fixed number of columns. The MIT notes even reference a vehicle driver or vehicle specialist example from a prior discussion that illustrates this concept beautifully.
Got it. So normalization is about moving towards more flexible and interconnected data structures. Now, let's talk about these normal forms. I hear about these. First normal form, second. We're starting with second normal form, or 2NF. What's the core principle we need to grasp here?
Okay, so the fundamental principle of 2NF is that all non-key fields in a table must be fully dependent on the entire primary key, not just part of it.
Okay, let's break that down a bit. What happens if a field only depends on part of the primary key? What's the issue there?
Right, so the MIT notes provide a really clear illustration. Imagine a table where the primary key is a combination of part and warehouse. So two fields make the key.
Part and warehouse, got it.
Now, maybe to make reporting seem easier, someone might add address to this table. However, the warehouse res is a fact that is true only about the warehouse, right? Not about the specific part that's stored there.
Oh, I see. The address depends only on the warehouse, not the part plus the warehouse.
Precisely. It's a dependency on only part of the key. Think of like a school registration, where the primary key is a student ID and a course code.
Okay.
It wouldn't make sense to store the teacher's home address in that table, right? Because the teacher's address isn't specific to that particular student taking that particular course. It's a fact only about the teacher or maybe the course itself. That's the kind of partial dependency 2NF aims to eliminate.
I see the problem. So you'd have the same warehouse address repeated for every single part stored in that particular warehouse. That definitely sounds like unnecessary redundancy.
Exactly. That's the big issue. A non-normalized table violating 2NF might look something like this. You'd have part 42, Boston, quantity 2000, address 24 main saint. Then part 333 Boston, quantity 1000, address 24 main saint again.
Repeating 24 mainstay.
Right. And then maybe part 390, New York, quantity 3000, address 99 Broad St.
Okay.
The solution in 2NF is to decompose this, to break it into two separate tables or entity types. An inventory table containing part, warehouse, and quantity, and then a separate warehouse table with just warehouse and warehouse address.
That makes perfect sense. The advantage is clear. We've eliminated that data duplication. The notes mention that a former disadvantage of this separation was needing to query two tables if you needed the address for a specific part in a specific warehouse. Is that still a significant concern in modern database systems?
That's a great question. The notes rightly point out that while this used to be a potential drawback maybe decades ago, modern database systems and their query optimizers are incredibly efficient at handling these joins between tables.
So it's fast enough now.
Yeah, the performance impact is often negligible, really. And the significant benefits of reduced redundancy and improved data integrity almost always outweigh this former concern. It's rarely an issue today.
Okay, good to know. Let's move on then to third normal form, or 3NF. What potential issues does this address in our database design? Built on 2NF, right?
Exactly, it builds on 2NF. Third normal form ensures that all non-key attributes are not dependent on other non-key attributes. So no jumping from one non-key field to another.
Okay. Dependency between non-key fields.
Yeah. The MIT notes highlight the potential for inconsistencies and difficulties in maintaining data when you try to cram multiple independent pieces of information, like, say, skills and languages for an employee, into a single row or table inappropriately.
Inconsistencies in terms of how the data is structured and updated, is that the idea?
Precisely. Imagine an employees table where you try to list all skills and languages in the same cell for each employee. For instance, one record for Brown might list cook, type under skills, and French, German under languages.
Right.
While another record for Smith might have type, cook, and German, Greek. The order in these lists, how you decide to combine them if someone gains a new skill, can lead to a lot of different possible arrangements and potential for errors or inconsistencies when you try to query or update this data. It gets messy.
It sounds like it could become quite unwieldy, yeah, especially as the number of skills and languages grows for each employee. Okay, now let's tackle fourth normal form, or 4NF. What's the core problem this aims to solve?
Right. 4NF deals with situations where you have multiple independent multi-valued dependencies within a single table.
Multi-valued dependencies. Okay.
The notes refer to this as a disjoint format, which in essence is like trying to represent two or more separate one-to-many relationships in a single structure. It's like forcing unrelated lists together.
And a key sign of this is ambiguity with blank fields.
Yes, exactly. A key indicator of a 4NF violation is the ambiguity that can arise from blank or null fields.
How can a blank field be ambiguous in this context? What could it mean?
Well, the notes provide several potential meanings for a blank skill field, for example. Does it mean the employee has no skills at all?
Okay.
Or that the skill attribute simply doesn't apply to this particular employee? Or perhaps the data is currently unknown.
Right, just missing for now.
Or even, as in our earlier skills languages example, that the information might be found in another related record within that same poorly structured table. It lacks a clear and unambiguous meaning.
That makes sense. A blank field could signify several different things depending on the context. The notes provide an example table that illustrates 4NF problems. Can you walk us through that?
Certainly. Consider a table structured like this, trying to capture both skills and languages for employees. Employee, skill, language.
Okay.
You might have Brown, cook, French, then another row, Brown, cook, German, and another Brown, cook, Greek.
Ah, so Brown the cook speaks 3 languages.
Right, but then you also have Brown type French, Brown type German, Brown type Greek.
So Brown the typist also speaks those same 3 languages. You see the repetition.
Exactly. And you'd have a similar set for Smith. The table explodes multiplicatively. As the notes explain, the 4NF solution is to decompose this into 2 separate tables.
Ah, makes sense.
One representing the employee skill relationship, Brown, cook, Brown type, and another for the employee language relationship, Brown, French, Brown, German, Brown, Greek. This clearly separates the 2 independent, multi-valued dependencies.
That definitely cleans things up, with one table dedicated to each distinct relationship, much clearer. But the notes also introduce a really interesting nuance. Normalization to 4NF might not be necessary if the skills and languages are inherently related. How would that work?
Yeah, this is a subtle but important point. If there's a genuine dependency between the attributes, for example, if our employee Smith only cooks French food and types exclusively in French and Greek, then the skills and languages are not entirely independent facts about Smith.
So the skill dictates the language, or maybe the language dictates the skill in some way.
Exactly. In this specific constrained scenario where a skill always implies a certain set of languages or vice versa, the original combined table might be acceptable because the seemingly multiple values are actually tied together by a business rule.
So it really hinges on the underlying business rules and whether these seemingly independent attributes are actually connected in some way.
Interesting. The notes also give some relatable real-world examples where 4NF issues might surface, like a person being involved in multiple projects and belonging to multiple departments.
Exactly. That's a classic one. If you try to represent all that information in a single person table with columns for project and department, you'd likely run into similar redundancy and update anomalies.
Right.
The notes emphasize that in problematic 4NF cases, you can't reliably reconstruct a complete record by looking at subsets of the data within that same table. It becomes ambiguous.
And the agent company product example really drives this point home. Even if current business rules prevent certain combinations, like Agent Smith not selling Ford trucks or GM cars, embedding those implicit rules within a single table structure can be a risky proposition for long-term data integrity, can't it? Precisely. Because as business rules inevitably evolve and change, that single, less normalized table can become a source of inconsistencies and errors. Breaking it down into agent company, company product, and maybe agent product, if the agent-product relationship isn't strictly derived from the other two, creates a much more flexible and robust foundation for your data. Handles change better.
Okay, almost there with normal forms. Finally, we arrive at fifth normal form, or 5NF. What new challenges does this address in database design? This one sounds even more obscure.
It is a bit more nuanced, yeah. 5NF tackles the issue of redundancy that arises when you can reconstruct a table from other related tables, but the schema doesn't explicitly enforce this dependency through keys, leading to potential inconsistencies. It's about avoiding redundant facts.
Redundant facts. Okay. The notes give an example of an agent product table.
Yes, where the fact that a specific agent sells a particular product might be repeated unnecessarily if it can be logically derived from other relationships, like which companies the agent represents and which products those companies make.
So a non-normalized table in this case might look something like Agent Smith, product car. Agent Smith, product truck. Agent Jones, product car. Agent Jones, product truck. Agent Brown, product car. Agent Brown, product bus. Something like that.
Exactly. You might have those pairings listed explicitly.
What are the practical downsides of this kind of repetition, this redundant fact listing?
Well, the notes highlight what's known as an update anomaly. If Agent Smith stops selling cars, you would need to find and update every single row where Smith is listed as selling a car. If you miss even one, your data becomes inconsistent.
Ah, okay.
Easy to make mistakes.
Very easy. Furthermore, as the number of agents and products increases, the size of this single table grows multiplicatively, whereas in a properly normalized 5NF design, often involving breaking it into agent company product tables, the increase would be more additive. For large-scale databases, this difference can have a significant impact on performance and storage. Right, that multiplicative growth can kill performance. And the implied fifth normal form solution involves a further decomposition, potentially into tables like agent company product, and then the agent product table would only be necessary if there are direct agent-product relationships that aren't solely determined by the companies they represent.
That's the general idea, yes. It ensures you're only storing facts that can't be derived from joining other tables. The notes also point out a critical challenge with this non-normalized structure. It becomes very difficult to quickly and accurately deduce the underlying business rules.
How so?
Well, looking at that combined table, you can see that Agent Jones sells cars and that GM makes cars. But you can't immediately infer from this table alone whether Jones represents GM.
Right, the link isn't explicit.
Similarly, you see Brown represents Ford and Ford makes trucks, but the table doesn't explicitly tell you if Brown actually sells trucks. The relationships are obscured.
It becomes much harder to understand the inherent relationships and constraints within the data. So, as we conclude our exploration of normalization, what are the key takeaways, the morals of this story, as the MIT notes eloquently put it?
Yeah, the notes offer some really powerful insights here.
Yeah.
Firstly, they emphasize that while the systems we build to manage data that be temporary, software gets replaced, the data itself often has a much longer lifespan.
Data is permanent. Systems are ephemeral.
Exactly. You can always rewrite a flawed system, but corrupted or inconsistent data can be incredibly difficult, if not impossible, to recover. And they share a rather alarming statistic,
Oh,
a reported 90% error rate in a real-world circuit design database.
90%.
90%. It suffered from a lack of proper normalization and allowed null foreign keys. This resulted in a fundamental mismatch between the way the data was structured and the actual business rules it was supposed to represent.
Wow.
It's a stark reminder of how crucial sound database design principles truly are in practice.
That's a truly sobering statistic, 90% errors. Okay, we've taken a deep dive into how to structure our data effectively with normalization. Now, let's shift our focus to how we actually work with that data once it's well organized. This brings us to SQL, the structured query language.
Indeed, SQL. It has become the standard language for interacting with relational databases. As Geeks for Geeks notes, it was developed by IBM back in the 1970s.
Wow, that long ago.
Yeah, it's been around. And it provides us with the tools to access and manipulate data, basically, to create, read, update, and delete information stored within these databases, the basic CRU'd operations.
It seems like SQL is a fundamental technology that underpins so much the software we use every day. Why has it become so ubiquitous? What makes it so successful?
Well, as Tutorials Point highlights, SQL is used in virtually every application software that deals with structured data. Think banking, finance, education, security systems.
Yeah.
It's everywhere.
Yeah.
The AWS explanation also points out its excellent integration capabilities with a wide range of different programming languages, making it an essential skill for developers and data analysts alike.
So it plays well with others.
Exactly. Plus, its reliance on common English keywords, as Tutorials Point mentions, makes it relatively accessible to learn compared to some other programming paradigms. It reads a bit like English.
Okay. So what's the fundamental way that a relational database, which SQL operates on, organizes information? We touched on tables.
Right. The core concept is storing information in tables, which you can think of as being similar to spreadsheets, basically.
Yeah.
These tables are composed of rows.
Records.
Exactly, records or entries, and columns, which define the specific fields or attributes for each record. Tutorials Point provides a simple example of a customer's table with columns like ID, name, age, salary, city, and country.
Pretty standard stuff.
Yeah, and the image we have access to further illustrates this, clearly showing how a row represents a complete record.
Yeah.
A column represents all the values for a particular field across all records. And a single cell at the intersection of a row and column is a field. It also introduces the important concept of an NLL value.
Ah, NL.
Which signifies missing or unknown data for a particular field in a record. Doesn't mean zero or an empty string, necessarily, just unknown.
Got it. Now, we often hear about different types of database systems, MySQL, SQL Server, PostgreSQL, and so on. Are they all speaking exactly the same SQL language? Or are there variations?
That's a key point. While they largely adhere to the ANSI SQL standard, which provides a common foundation, there are various relational database management systems, or RDBMS, each with its own extensions and specific features, its own dialect, if you will.
Dialects occur.
Tutorials Point gives us a good overview of some of the most popular ones. So while there are many options, the underlying principles of SQL we've discussed will apply to most of them, though the specific flavor might have its own quirks, as we'll touch on later.
Like MySQL, for example. That's a really common one.
Yes. MySQL, which has a history involving Sun Microsystems and later Oracle, is widely recognized for its high performance, excellent availability, strong scalability, and robust data protection features. Very popular, especially for web applications.
And what about Microsoft's primary database offering?
That would be MS SQL Server, developed by Microsoft. It primarily uses T-SQL, which is its own dialect that extends the standard ANSI SQL with additional features.
T-SQL, right. Oracle is another major player in the database world, isn't it? Often seen in big enterprises.
Absolutely. Oracle has a long and significant history, being the first commercially successful SQL-based database system. It's renowned for its advanced features like sophisticated concurrency control mechanisms, read consistency guarantees, and robust locking capabilities, making it suitable for very demanding enterprise applications. Very powerful, but can be complex.
And then there's PostgreSQL, which is often highlighted for being an open source and highly accessible option. Seems very popular, too.
PostgreSQL is indeed a powerful open-source RDBMS. It's known for its adherence to standards, its support for advanced data types, and its strong emphasis on resilience, data integrity, and correctness. People often praise its robustness.
Okay.
Tutorials Point also mentions some key version releases that introduced important features like logical replication and table partitioning, showcasing its ongoing evolution and commitment to advanced functionality. It keeps getting better.
SQLite is another database system that often comes up, especially in embedded applications or mobile apps. What's its niche?
SQLite is a fascinating case. It's an open-source library written in ANSIC that provides a lightweight, cross-platform, and serverless SQL database engine. Basically, the database is just a file.
Serverless. Interesting.
Yeah, despite its simplicity, it supports atomic, consistent, isolated, and durable ACS transactions, making it surprisingly reliable, even in situations with potential system crashes. Great for single-user or low concurrency situations.
And for those working within the Microsoft ecosystem, maybe smaller projects, there's MS Access.
Right, MS Access is a desktop-based RDBMS from Microsoft that's particularly known for its user-friendly graphical interface. It bundles the database engine with tools for creating forms and reports. It makes it a popular choice for smaller-scale database applications and for users who prefer a visual approach to database management. Less common for, say, web backends.
Okay. So with all these different database systems, what are some of the fundamental actions we can perform using SQL across them? The core commands.
Well, Tutorials Point introduces some core SQL commands that fall into two main categories. First, we have DDL, or Data Definition Language.
A DDL definition.
Right. This includes commands like create, used to define the structure of database objects like tables, and GIP, used to remove them entirely. It's about the structure.
Okay.
Second, there's DML, or Data Manipulation Language.
DML manipulation.
Yep. This allows us to work with the data itself. This includes commands like select to retrieve data from tables.
The most common one, probably.
Absolutely. Then insert to add new records, update to modify existing records, and delete to remove specific records based on certain conditions.
Create, read, update, delete, CR read.
Exactly. And finally, truncate is another DML command used to quickly remove all rows from a table without logging individual deletions. Faster than delete for clearing a table.
Got it. Let's focus on getting information out of these tables. How do we construct SQL queries to retrieve the specific data we need? The select statement.
Right. The heart of data retrieval in SQL is the select statement. Tutorials Point provides a very straightforward example. Select from customers where country equals USA.
Okay, select star from customers where country equals USA.
Exactly. This query instructs the database to retrieve all columns, that's from the customers table, but only for those rows where the value in the country column is USA. It's quite readable.
It is. And they mention an online editor for practice.
Yeah, they highlight their online SQL editor as a valuable tool for practicing writing and executing these kinds of queries directly in your web browser. Really helpful for learning.
Now, what happens when the information we need is spread across multiple related tables? That normalization work we did earlier, that's where the concept of SQL joins comes into play, right?
Exactly. SQL joins are a fundamental tool in relational databases that allow you to combine data from two or more tables based on a relationship between specific columns in those tables. You need joins to put the normalized data back together.
Makes sense.
TidyB provides a really comprehensive explanation of the different types of joins and how they work.
What are the most common types of joins that someone working with SQL should be familiar with? I hear inner, outer.
Yeah, the common types include inner join. This one returns only the rows where there's a matching value in the specified columns of both tables you're joining. Only the matches.
Okay, only where both tables have related data.
Right. Then we have left join, sometimes called left outer join. This returns all rows from the left-hand table and the matching rows from the right-hand table.
Oh, from the left.
Yes. If there's no match in the right table for a row on the left, it fills in NLL values for the columns from the right table.
Okay, so you don't lose rows from the left table.
Correct. Right join, or right outer join, is the mirror image. It returns all rows from the right table and the matching rows from the left table, with NLs for non-matches in the left table.
Same idea, just flipped.
Exactly. Then there's full join, or full outer join. This combines the results of both left and right joins. It returns all rows when there's a match in either table, and NLLs where there isn't a match on either side. Keeps everything from both tables.
Okay, the most inclusive one.
Pretty much. And finally, cross join. This produces what's called a Cartesian product. It returns every possible combination of rows from the two tables. If one table has 10 rows and the other has 5, you get 50 rows.
Wow, every combination. When would you use that?
It's less common, but often useful for generating all possible pairs of data, maybe for testing or setting up some initial data structures.
Okay. When would you typically use each of these different types of joins in practical scenarios, like inner versus left?
Well, TDB outlines some typical use cases. Inner join is your go-to when you only want to see data that has corresponding entries in both of the tables you're combining, like finding customers who have placed orders.
Right, you need both customer and order info.
Exactly. Left or right joins are invaluable when you need to ensure that you retrieve all the records from one specific table, regardless of whether there are matching records in the other table, like listing all customers and their orders, even if some customers haven't ordered anything yet.
Ah, so you see the customers with NOL for the order details.
Precisely. This is common in reporting scenarios. Full join is less frequently used, but can be helpful when you need a complete picture of all records from both tables, highlighting where matches exist and where they don't, maybe comparing two lists.
Okay.
And cross-join, as we said, useful for generating all possible combinations, maybe for creating a schedule or pairing up items.
Got it. Are there any best practices or tips for writing efficient SQL joins? They can get complex.
Absolutely. TDB emphasizes a few key considerations. First, always aim to select only the specific columns that you actually need in your result set. Avoid using select if you can, especially with joins. It's just wasteful.
Select only what you need. Makes sense.
Second, try to filter your data using the where clause as early as possible in your query execution plan. Filter first, then join, if possible. This reduces the amount of data that the join operation has to process.
Filter early. Good tip.
And finally, it's crucial to carefully choose the correct type of join for the specific logical relationship you're trying to represent between your tables. Using the wrong join can give you incorrect results or poor performance.
Right. Tool for the job. Okay, let's move on to SQL subqueries. What exactly are they, and when might we find them useful in our queries? Nested queries, right?
Exactly. Subqueries, also known as nested queries or inner queries, are SQL queries that are embedded within another larger SQL query. DataQuest provides a really good beginner's guide to understanding them.
So a query inside a query.
Yep. One of the most common uses for subqueries is within the where clause of a main query. Here, the subquery is executed first, and its result, which could be a single value or a set of values, is then used to filter the rows returned by the main query.
How would that work? Give me an example.
Sure. You might first use a subquery to find, say, all the customer IDs for customers who have placed orders totaling more than $1,000.
Okay, the subquery gets the list of IDs.
Right. Then you use that list of customer IDs in the where clause of your main query to retrieve other information, like the names and addresses, only for those specific high-value customers.
I see. So it's like performing a preliminary query to get a set of criteria that the main query then uses.
Precisely. DataQuest also mentions that subqueries can be used in other parts of a SQL statement as well. For instance, you can use them in the from clause.
In the from clause? How?
Yeah. The results set of the subquery is treated as a temporary table that the outer query can then work with. It's like creating a mini table on the fly just for that query. You can even use subqueries in the select list to retrieve a single calculated value for each row in the main query, although they caution that doing so can sometimes impact query performance if not used carefully. But they provide a practical example of using subqueries to find employees who support customers with total purchases exceeding $100.
Okay, so powerful, but used with care. Now, to ensure that the data in our tables remains consistent and adheres to certain rules, we use SQL constraints, right? Like rules for the columns.
Exactly. SQL constraints are rules that you define on the columns of a table to enforce data integrity and maintain the quality of the data. Geeks for Geeks lists several fundamental constraint types.
Like what?
Well, not NL ensures that a particular column cannot contain any missing or null values. You must provide a value.
Okay, mandatory field.
Unique enforces that all values in a specified column or set of columns must be distinct. No duplicates allowed.
Like an email address or username.
Exactly.
Right.
Primary key serves to uniquely identify each record within a table. It inherently implies both not NL and unique. It's the main identifier for a row.
The unique ID for each row.
Right. Foreign key is crucial for establishing and enforcing relationships between different tables. It ensures that a value in one table matches a primary key value in another table, maintaining that link we talked about with normalization.
So it connects related tables.
Yes, enforces the relationship. Check constraints allow you to define specific conditions that the values in a column must satisfy, like maybe a price column must be greater than 0.
Custom rules.
Yep. And finally, default constraints allow you to specify a default value that will be automatically assigned to a column if no value is provided during data insertion, like setting a status to pending automatically.
Handy for default.
Okay.
We also hear about SQL aggregate functions. What role do they play in data analysis? Summarizing data.
Exactly. Aggregate functions perform calculations on a set of values within a column and return a single summary value. Geeks for Geeks mentions several commonly used aggregate functions, such like count, to determine the number of rows that meet certain criteria, SUM to calculate the total sum of values in a numeric column, AVG to find the average value, MIN to identify the smallest value, and max to find the largest value within a set of data. Really common for reporting.
Count, sum, average, min, max. Got it. We previously discussed the where clause for filtering individual rows. How does the having clause differ in its purpose? They both seem like filters.
That's a common point of confusion, but Geeks for Geeks clearly distinguishes between the two. The where clause is applied before any grouping of data takes place using group by Y. It filters out individual rows before aggregation.
Okay, where filters rows first.
Right. In contrast, the having clause is used to filter groups of rows after they have been grouped together using the group by Y clause and after aggregate functions have been calculated.
Ah, having filters the results of the aggregation.
Precisely. So where operates on individual records,
Yeah.
while having operates on aggregated results. You use having to filter based on the results of count, SU, AVG, etc.
Okay, that clarifies it. To improve the speed at which our queries retrieve data, we can utilize SQL indexes, correct? Like an index in a book.
Yes, that's a great analogy. SQL indexes are special lookup tables that the database search engine can use to speed up data retrieval. Geeks for Geeks notes that they allow the database to locate specific rows much faster without having to scan through the entire table, just like using a book index saves you from reading every page.
Makes queries faster. Any downsides?
Yes, it's important to remember that there's a trade-off. Indexes do require additional storage space within the database.
Okay, they take up space.
And they can slightly slow down data modification operations like inserting, updating, or deleting rows. Because whenever you change the data, the index also needs to be updated to stay accurate.
So faster reads, but slightly slower writes. Trade-off.
Exactly.
Yeah.
You need to index strategically on columns used frequently in where clauses are joined.
What's the fundamental difference between using the delete statement and the truncate statement to remove data from a table? Both get rid of rows.
They do, but in very different ways. Geeks for Geeks explains that delete is a row-by-row operation. When you use delete, the database records information about each row being removed in its transaction logs.
Okay, it logs each deletion.
Right. This allows for the possibility of rolling back the deletion if needed, and crucially, it also allows you to use a where clause to specify exactly which rows you want to remove. You can delete specific records.
Selective deletion with delete.
Yes. Truncate, on the other hand, is a much more drastic operation. It removes all rows from a table at once and does not log individual row deletions or logs it minimally,
All rows, no logging.
which makes it significantly faster for clearing out large tables. But it also means that the operation usually cannot be rolled back easily, and you cannot selectively remove rows using a where clause. It's all or nothing.
Use truncate with caution then.
Definitely.
And finally, to present our retrieved data in a more organized and readable format, we can use the order Y clause. Pretty straightforward.
That's right. As Geeks for Geeks mentions, the order by Y clause allows you to sort the result set of your query based on the values in one or more columns. You can specify whether you want to sort the data in ascending order, ASC, which is the default, or descending order, DESC, making it easier to analyze and interpret the retrieved information. Simple, but essential.
We previously discussed how normalization aims to reduce data redundancy. Are there situations where we might intentionally introduce redundancy through a process called denormalization? Seems counterintuitive.
It does seem counterintuitive at first, but yes, denormalization is a technique where you intentionally add redundancy back into a database design. You might combine tables or add redundant data to existing tables.
Why on earth would you do that after all the effort of normalizing?
Performance. As Geeks for Geeks points out, the primary motivation behind denormalization is to improve the performance of data retrieval, particularly for complex queries that involve numerous joins across many normalized tables. Sometimes doing those joins frequently can be slow.
So you sacrifice some normalization purity for speed.
Exactly. You might pre-join some data or duplicate a frequently needed field to avoid a costly join in a critical query. The trade-off, of course, is the potential for increased data redundancy and the added complexity of ensuring data consistency across the denormalized structure. You have to update the redundant data everywhere it exists.
Right. More places for data to get out of sync. Another trade-off. Okay. Reliability and consistency are paramount for any database system. Can you briefly explain the ACD properties that are often associated with database transactions, ACID?
Sure. ACD is an acronym that represents 4 key properties of reliable database transactions: atomicity, consistency, isolation, and durability.
Okay, what do they mean?
Atomicity means that a transaction is treated as a single, indivisible unit of work. Either all of its operations complete successfully or none of them do. No half-done transactions.
All or nothing. Got it.
Consistency ensures that a transaction brings the database from one valid state to another. It doesn't violate any integrity constraints.
Keeps the data valid according to the rules.
Right. Isolation means that concurrent transactions occur without interfering with each other. It should seem as though transactions are executed one after another, even if they're happening at the same time.
No stepping on each other's toes.
Exactly. And durability guarantees that once a transaction has been successfully committed, its changes are permanent and will survive any subsequent system failures, like crashes or power outages.
Committed means permanent.
Yes. As MongoDB explains, these properties are essential for ensuring that database transactions are processed in a dependable manner, maintaining the integrity of the data even in the face of errors or system failures. They are particularly critical for applications that handles sensitive or regulated data like financial transactions. You absolutely need ACD guarantees there.
Absolutely. And how do NoSQL databases like MongoDB approach these concepts of data reliability and consistency? They're different architecturally, aren't they?
They are often different, yes. While our main focus today is on SQL and relational databases, it's important to understand that NoSQL databases like MongoDB have their own mechanisms for ensuring data reliability and consistency. Their approaches might differ from the traditional ACD properties of relational databases, sometimes offering more flexible or tunable consistency models.
So maybe not strictly ACDs sometimes.
Sometimes not in the same way across all operations, or they might offer different levels of consistency you can choose. MongoDB's documentation, for example, explains how it achieves these goals through features like multi-document transactions, which are ACD, and various read-write concerns that let you tune the consistency versus performance trade-off. The fundamental goal of ensuring data integrity remains a priority, but the implementation details can vary.
Okay, different approaches to the same goal. Lastly, for both optimizing performance and enhancing security, we often hear about the importance of using parameterized queries and stored procedures. Why are these considered best practices?
Right. Both parameterized queries and stored procedures offer significant advantages in terms of both performance and, crucially, security.
How do they help performance?
As Excel Data and Geeks for Geeks explain, parameterized queries, also known as prepared statements, allow the database system to compile and optimize the query execution plan once, and then reuse that plan for multiple executions with different input values. This reduces query processing overhead and improves performance, especially for queries run frequently.
Compile once, run many times, faster.
Exactly. And stored procedures, which are pre-compiled SQL code stored directly within the database, can also enhance performance by reducing the amount of SQL text sent over the network and potentially allowing for better optimization by the database itself.
And the security aspect, this is about SQL injection, right?
Yes, absolutely critical. As OWASP emphasizes, parameterized queries are a crucial defense mechanism against SQL injection attacks. By treating user-supplied input strictly as data, not as executable code, they prevent malicious users from injecting their own SQL commands into your database queries. The database knows what's code and what's data.
Separating code from data, that's the key.
That's the key. Stored procedures can also help, especially if they are written carefully and don't construct dynamic SQL inside themselves using user input. They can provide a more controlled interface to the data.
Okay, so parameterized queries and stored procedures. Good for speed, essential for security. Got it. So we've covered a lot of ground on how to write and manage SQL queries. Now let's delve into some best practices to ensure our SQL is not only functional, but also efficient and secure. Where do we start?
Well, as Metabase rightly points out, a crucial first step, maybe the crucial step in writing effective SQL, is to thoroughly understand your data.
Know your data first.
Yes. Before you even begin to write a query, take the time to study the metadata, examine the table structures, understand the relationships between different tables, know what the columns mean, what kind of values are in there. This foundational understanding will guide your query design and help you avoid common pitfalls. Don't just start typing select lists.
Good advice. What about the order in which the different parts of a SQL query are typically executed? Does understanding this execution order have implications for query optimization? You mentioned filtering early.
Absolutely. Metabase outlines the logical order of operations in a SQL query. It generally starts with the from and join clauses to determine the tables involved.
Get the tables.
Then the where clause filters the rows based on conditions,
Filter the rows.
followed by group by for aggregation,
And group them up.
then having to filter the group results.
Filter the groups.
Then select to choose the specific columns to return.
Pick the columns.
Union if you're combining results from multiple queries.
Combine sets.
And finally, order by Y to sort the output.
Sort at the end. Okay, from, where, group by, having, select, order by, roughly.
Right. Now, the database's query optimizer might rearrange this order internally for efficiency, but understanding this logical flow helps you write more effective queries, especially when it comes to the principle Metabase emphasizes. Eliminate unnecessary data as early in the process as possible. Use that where clause effectively.
Filter early, filter often. What are some other general guidelines or best practices that we should keep in mind when writing SQL queries?
Metabase shares several valuable guidelines. First, comment your SQL code, especially to explain the why behind complex logic or specific filtering conditions. Future you or someone else will thank you.
Good point. Comments are key.
When working with joins, always use the explicit on keyword to clearly define the join conditions. Avoid the old comma-style joins. Explicit is better than implicit.
Use join insel.
Be cautious about applying functions directly to columns in the where clause, like where upper last name Smith,
Why is that bad?
because it can often prevent the database from using indexes effectively on that last name column. The database might have to calculate the function result for every single row before checking the condition. This is known as creating non-sargable queries.
Non-sargable. Okay, avoid functions on columns in where if possible.
Right. Try to transform the other side of the comparison if you can. Whenever possible, prefer using the operator for exact matches rather than the like operator with wildcards, as equality comparisons can often leverage indexes more efficiently.
Is faster than like.
Often, yes, for index columns. Also, when using like, avoid leading wildcards, like where name like Basin Smith.
Yeah.
This usually forces the database to perform a full table scan because the index can't be used effectively if the search doesn't start from the beginning of the string.
Avoid bleeding percent.
And when you need to check for the existence of a value in another table or subquery, the exists operator is generally more performant and semantically clearer than using in with the subquery in many database systems.
Prefer exists over in for subqueries. Interesting.
Yeah, it often performs better because it can stop searching as soon as it finds the first match.
We know that indexes are crucial for query performance. Are there any best practices we should follow when it comes to creating and using them? Beyond just avoiding functions in where?
Definitely. For columns that are frequently used together in where clause conditions or in join clauses, consider creating composite indexes that include all those columns in the appropriate order, as Metabase suggests.
Composite indexes for multiple columns used together.
Yes. And one of the most powerful tools for understanding how your database is actually executing your queries and identifying potential performance bottlenecks is the explain command.
Explain.
Or explain analyze in PostgreSQL and some others. It shows you the query execution plan, how the database intends to fetch the data, which indexes it plans to use, how it will perform joins, etc. It's essential for serious query tuning.
So explain helps you see under the hood.
Exactly. It lets you diagnose slow queries.
We've highlighted the significant security risk of SQL injection. What are the most effective ways to protect our databases from this type of attack? We mentioned parameterized queries.
Yes. And OWASP, the Open Web Application Security Project, strongly emphasizes that this is the primary defense. The most effective way to prevent SQL injection vulnerabilities is to avoid building dynamic SQL queries by directly concatenating user-supplied input into your SQL strings. Just don't do it.
Don't stitch SQL together with user input.
Never. Instead, you should consistently use prepared statements, also known as parameterized queries. The SQL code and the user-provided data are treated completely separately by the database driver and engine.
Okay.
OWASP provides clear examples, such as the Safe Java prepared statement, which demonstrates how to pass user input as parameters to a predefined SQL structure. The database knows the input is just data.
Parameterized queries are the way. What about stored procedures?
Stored procedures, if implemented with care to avoid dynamic SQL construction within them using user input, can also offer a layer of protection by creating a controlled API to the database. But parameterized queries are generally the most recommended approach for application code.
Got it. Beyond just preventing SQL injection, what are some general best practices for ensuring the overall security of our database systems, access control and stuff?
Right. OWASP also stresses the fundamental security principle of least privilege.
Least privilege.
Grant each application or user account only the absolute minimum level of permissions necessary for it to perform its required tasks. Never, ever grant DBA, database administrator, or administrative privileges to application accounts that don't genuinely need them. That's a huge risk.
Only give the permissions needed, nothing more.
Exactly. Consider using database views to restrict an application's access to only specific columns or rows within tables, rather than granting full table access.
Views for limited access.
Additionally, you can restrict application accounts to only being able to execute specific stored procedures that they are authorized to use, rather than allowing direct table access. And a good security practice is also to use distinct database users for different web applications.
Different apps, different users. Why?
So that if one application is compromised, the attacker hopefully only gains access to that application's data, limiting the potential damage to other applications and their data. Containment.
Smart. Defense in depth. Are there specific techniques we can employ to make our SQL queries run faster and what's commonly referred to as SQL tuning? We mentioned indexes and explain.
Absolutely. SQL tuning is a huge field, but Data outlines several core techniques. These include ensuring you have appropriate indexes in place and that they're being used, restructuring complex queries to be more efficient, maybe breaking them down or rewriting joins, carefully selecting the right types of joins for your specific needs.
Basic blocking and tackling of query writing.
Right. Optimizing your existing indexes, maybe they need rebuilding or tweaking. Optimizing the use of joins and subqueries within your queries. Sometimes the order matters. Reducing the number of unnecessary columns you select again, and minimizing complex calculations within the query can also lead to significant performance improvements.
Do less work in the query.
Exactly. And as we discussed earlier, using parameterized queries and stored procedures also contributes to better performance through planned caching.
What about some more advanced or less commonly discussed SQL tuning methods for really tough queries?
Well, Data mentions more advanced techniques like using hints.
Hints, like telling the database what to do.
Sort of, yeah. Hints are directives you can embed in your SQL to try and influence the database's query optimizer in making better execution plan choices. For example, suggesting which index to use or what join method to employ.
But you have to be careful with those.
Extremely careful. They can sometimes have unintended consequences or become outdated as data or the database version changes. It overrides the optimizer, which is usually pretty smart. They also touch on being careful when using dynamic SQL optimization, leveraging partitioned views for very large data sets to allow the database to query only relevant partitions.
Partitioning for huge tables.
Right, and using materialized views. These store the pre-calculated results of complex queries, allowing for much faster retrieval of frequently needed aggregated data, but you need a strategy to keep them refreshed.
Materialized views for pre-calculated results. Okay. And what are some fundamental best practices that we should consistently follow for SQL tuning, like daily habits?
Data recommends consistently monitoring the performance of your frequently used and critical queries. Don't wait for things to break.
Monitor performance.
Using the limit clause or equivalent to restrict the number of rows returned, especially during development and testing, is a good habit. Avoid pulling back millions of rows accidentally.
Use limit. Sensible.
Avoiding select and only selecting the columns you actually need, we keep saying it because it's important, reduces I/O and network traffic.
Don't use select. Got it.
Proactively managing your database indexes, identifying unused ones that are just slowing down writes, and creating new ones as query patterns change is essential. Indexing isn't a one-time task.
Manage indexes actively.
And as we've emphasized, always parameterize your queries to improve both performance and security. Make it a default habit.
Parameterize everything.
Okay. Now, as we've touched on throughout our discussion, there isn't just one monolithic version of SQL. There are different flavors or dialects. How significantly do these SQL dialects differ from one another in practice? Is it a big deal?
It can be, yeah. The Reddit discussion we looked at really highlights the practical realities of SQL dialects. While a significant portion, maybe around 95% of basic SQL syntax and functionality, might be consistent across different database systems like MySQL, PostgreSQL, SQL Server, Oracle.
So most basic stuff is the same, mostly, yeah. But that remaining 5% where they diverge can often be a source of considerable frustration and extra work, especially when you're trying to write code that works across multiple database platforms or migrating between them. That 5% can be a real pain.
So the fundamental select statement for retrieving data, like select columns from table where condition, is generally going to work the same way across most systems.
Yes, basic select syntax for retrieving columns and filtering rows with where is usually quite universal, pretty standard.
Okay.
However, as the Reddit thread points out, you start to see differences in syntax for common tasks, like limiting the number of rows returned or specifying an offset for pagination.
Ah, like getting page 2 of results.
Exactly. For example, while the limit clause is widely used in many SQL databases like MySQL and PostgreSQL, limit 10, offset 20, SQL Server historically used select top 10, and later introduced offset fetch next rows only. Although a standard offset and limit syntax was introduced in the SQL 2008 standard, not all systems implemented it immediately or in the same way.
So even something basic like limiting rows can differ.
It can, yeah. Where else do these SQL dialects tend to have significant variations that developers and database administrators need to be aware of? Functions are a major area where SQL dialects can differ
Your
substantially.
functions, like for math or text.
Exactly. The Reddit discussion emphasizes that functions for performing tasks, like regular expression matching, date and time manipulation, this one is notorious, string operations, concatenation, finding substrings, mathematical calculations, they can vary quite significantly in both syntax and available functionality between different database engines.
So code using specific functions might not work if you switch databases.
Very likely not without changes. This can make it quite challenging to write SQL code that is easily portable across multiple database systems. Even aspects like how the query optimizer within each database engine works and the specific optimization techniques it employs can differ greatly, even between different versions of the same database system.
Wow, even versions matter for optimization.
Well, yeah, as illustrated by the example mentioned of Common Table Expression, CTE, optimization, behaving differently in older versions of PostgreSQL compared to newer ones.
So while having a solid understanding of core SQL principles provides a strong foundation, truly mastering a specific database engine requires dedicated experience and familiarity with its particular dialect and features. It's not just knowing SQL.
Exactly. That's the key takeaway from that discussion. The contributors to the Reddit thread overwhelmingly agree that while knowing SQL provides a valuable baseline skill, becoming truly proficient with a particular database system, like becoming a real SQL Server expert or a PostgreSQL guru, often takes years of hands-on experience and a deep understanding of its specific dialect, its unique features, its performance characteristics, and its common pitfalls.
Makes sense. Years of experience.
The discussion also touches on the increasing importance of being able to work with semi-structured data within relational databases, using features like SQL plus JSON.
Handling JSON inside SQL.
Right, that's becoming more common. And they mentioned the numerous online platforms available now for practicing your SQL skills in various environments, which is great for learning.
Good resources out there. Finally, how does the world of SQL-based relational databases compare to the landscape of NoSQL databases that we briefly mentioned earlier in our discussion? Just a quick contrast.
Sure. The AWS explanation provides a good high-level comparison. SQL offers a standardized and largely uniform language, despite the dialects, for manipulating structured data in tables with predefined schemas.
SQL standard language, structured data, schemas.
Right, whereas the approaches to data manipulation in NoSQL databases tend to be much more dependent on the specific NoSQL technology you're using. MongoDB's query language is different from Cassandra's, which is different from Redis commands. And they often work with more flexible data models like documents, key-value pairs, or graphs, often without rigid schemas.
NoSQL. Varied languages, flexible data models, often schemaless.
Exactly. SQL databases are often the preferred choice for transactional applications where strong ACID consistency and a well-defined schema are critical, as well as for analytical applications that require complex querying and reporting on structured data.
SQL for transactions and complex analysis on structured data.
Yeah. NoSQL databases, on the other hand, are often favored for applications that require massive scalability, high responsiveness, need to handle very large volumes of rapidly changing data, or benefit from those more flexible and schemaless data models. Think big data, real-time web apps, content management.
NoSQL for scale, speed, flexible big data.
That's a good summary. And just to reiterate, SQL Server is Microsoft's flagship relational database management system that utilizes the SQL language, specifically its own T-SQL dialect.
Gotcha. Phew. This has been an incredibly comprehensive deep dive into the fascinating world of databases and SQL. Let's quickly recap some of the key insights we've uncovered for our listeners.
Certainly. We've explored the fundamental importance of normalized database design, breaking data down logically as a way to prevent data errors, minimize redundancy, and ultimately create more reliable and maintainable systems in the long run. Remember that 90% error rate?
Can't forget that.
We've delved into the power and versatility of SQL as the standard language for interacting with and manipulating data with relational databases, your tool for getting data in and out. We've covered essential best practices for writing SQL queries that are not only correct but also efficient, filter early, index wisely, avoid select, and secure.
Parameterizing.
Efficiency and security are key.
And finally, we've highlighted the fact that while core SQL concepts are widely applicable, it's crucial to be aware of the differences, those tricky 5% that exist between various SQL dialects used by different database systems. Know your specific engine.
Whether you're just starting to explore the world of data or you need to get up to speed on these concepts for a meeting or, to better understand your field, this knowledge is truly invaluable for anyone working with technology today, isn't it? I really think so. It underpins so much. This brings us to a final thought for you to consider.
Okay, leave us with something to chew on.
In a world where the volume and variety of data continue to explode, and where we're increasingly relying on AI-driven tools for data management, how might the fundamental principles of database normalization, that structured approach, and the flexibility of SQL need to adapt and evolve?
Structure versus AI and big data.
Yeah, think about the ongoing interplay and balance between structured relational models, which give us consistency and integrity, and the more flexible non-relational approaches as we move further into the future of data management. Where does that balance lie going forward?